It's time to begin. All right, we have today and tomorrow, followed by a review and then an exam. I have an assignment due tomorrow, and we'll get another assignment at some point. There's also our ongoing project that the due date is rapidly approaching. That's something from Friday. Who started on CYK? Awesome. The rest of you have something fun to do over the next few days. Trying to do that over 1 week might be a bit of a challenge. So I would recommend thinking about getting started reasonably soon. Yesterday we finished the concepts of context-free languages, just looking at whether they're closed under certain operations. We found that they were closed under things like union and concatenation, but weren't closed under intersection. So that was interesting. We're going to look at another class of languages. We're going to take a pretty deep dive into this one because it is very important to the history of computer science and, turns out, the modern computer. So we've seen two classes of languages now. We've seen regular languages and context-free languages. When we're looking at the state machines for this, the only difference there was the inclusion of a stack, whether we brought a stack along with us or we didn't have any storage at all. And the fact that we could now take a stack with us meant that we could recognize a bunch of new types of languages that we couldn't recognize before. That was cool. The question moving forward, what are other language classes? And how could we come up with an automaton or a state machine to try to handle those more complicated languages? The first thing you might think of is what happens if instead of one stack, we could bring along two stacks with us? What do we think? Does that increase the power of the languages that we could represent? Does it change the languages that we could represent? Would this be something interesting worth pursuing?
It would only really change it in very specific circumstances.
Yeah. It ends up not remotely being interesting, which is interesting in and of itself, that it's not particularly interesting. There's not really a new class of languages. There is additional power here, but it's not meaningful additional power. It doesn't allow us to do something that we couldn't have done before. What about three stacks? Same thing. A queue instead of a stack? That's kind of the same as the two stacks question, because you can use two stacks to emulate a queue. What do we think? Any other ideas? Going back to data structures that we've seen, is there something that we have not utilized that we could utilize with regards to a state machine?
Array.
Using an array of some kind?
Ring.
Sorry?
A ring.
A ring. Interesting.
I have no idea how that would be useful, but it's a thought.
How so? Or maybe you can elaborate on what would a ring be and or do?
Something essentially like a queue, but rather than ending at a start, or having a start point and an end point, it would have
More a circular queue?
Yeah, essentially.
Yeah, okay. So instead of having a start that goes on forever, maybe we have the ability to expand the circle, but also read through to an end and cycle back to a beginning. Interesting idea. It turns out that as we start to think about this, we quickly run into a dead end. That no matter what we add to this, we don't really increase the allowable power of languages that we can represent. There was one exception to this. The most powerful possible automata was invented in, I think, the 40s, and has been the basis for the modern computer. That, of course, is the Turing machine. So there is no way to make an automata more powerful than a Turing machine. There are ways that we can make a Turing machine more efficient, but not change the languages that it can represent. So let's talk about this idea of a Turing machine. We have an infinite one-dimensional array. So there's no beginning and there's no end to this array. It goes on forever in both directions. Each cell of this holds a single input symbol or written symbol on it. We call this the tape. And this tape can be read from by a read-write head and written to with that same read-write head. So we can read from and write to the storage tape. What's nice about both being able to read and write individual tapes or individual cells is that we can move back and forth however much or little we want. We're relaxing the restriction of we get a single pass left to right on the input string. We can now do anything. There is no input or output other than the tape. What this means is all of the input to this is going to be on the tape prior to beginning the state machine. And the output to this machine is what is on the tape at the end of termination, at the end of the program. So a visual for this. We have our control unit, our series of states and transitions. That's inside of the control unit. Then there is a read-write head that is pointing to a cell of the tape that it is currently looking at. And it can move the read-write head along the tape. It can read a piece of information from the tape. It can write a piece of information to the tape. And it will do that according to the transition function defined inside of the control unit. Kind of like we have seen before, but the only real difference now is this input-output tape and this read-write. Formal definition of a Turing machine. We're up to 7 elements now. Inside of the control state, the control unit are the set of internal states, just like we've seen before. We have the input alphabet, just like we've seen before. There is the tape alphabet, which is similar to the concept of this alphabet in NPDAs. It's the symbols we can read and write. We then have the transition function that's defined as the transitions between the states that are in the internal state. We have a special symbol we're going to call the blank. And this is what is, by default, written on all cells that are not part of the input. So think of the blank kind of like a null. It's a symbol that represents that there is nothing there. We then have definitions for the initial state and the set of final states. And the transition function now, instead of specifying just in the regular languages, we specified just the from state and the to state and the character that was being read. And in NPDAs, we had the from state, the to state, the character that was being read at the top of stack symbol. And then we had to determine what was popped from that based on that top of stack symbol and then was pushed back on the stack. So that was everything that was needed for the transition function. Here we have a state and a tape alphabet pair. So what is on the tape symbol that we are currently on, and what state are we in? That is the input. The output to the transition function is a new state, a character to write to the input tape, and whether we are moving left or right on the input tape from the current position. So that's what that transition function on the bottom there is saying. So to begin the transition, state what's on the tape. So a state and a read. And then we have a to state, a write, and a move either left or right. Questions on the formal definition? Let's give you an example. Very basic Turing machine move here. We're starting in at state Q0, and the read-write head is looking at this leftmost cell, this A. And if we're using the transition here that says from Q0, when there is an A on the tape, we're going to move to Q1, write a D, and move right. That tells us that between the read, we're moving from Q0 to Q1. That's the from Q0 to Q1. We are reading an A, but we are writing a D by the time this has completed. What is on the input-output tape here at that same location is a D instead of an A. We overwrote the A with a D. Then we also moved right, so the read-write head is no longer pointing at the cell that used to contain the A, it's pointing at the cell that contains a B. Questions how all of that is embedded in the transition function definition, or what that means with regards to what this machine is doing? Just a before and after picture. So what is this thing? What is a Turing machine? It's a way of representing a simple computer. Do we agree that when we write a program, we are just writing a bunch of characters? It is very much like an input tape. We just write a bunch of characters. Those characters get combined into what we call tokens. Those tokens get parsed into what we're going to consider to be aspects of a grammar that can be combined together to make statements. Those statements become execution instructions, and then they dictate what the machine should do. It's programmable. We can write instructions, and those instructions can be read and then executed. So we have a CPU with finite memory. The finite memory is embedded in the states that we are declaring. So the control unit only has a finite number of states. You can't make an infinite state machine. The tape is our secondary storage. It's basically our hard disk or our RAM or whatever you want to consider to be storage. They're both storage. But note that the Turing machine can only carry out very few or very limited instructions. It can read a single character, write a single character, and move one space, and do that over and over and over. So it can read a symbol on the tape, knows what's there. Using that, it knows which transition to make in the control unit. And what can it actually do? It can rewrite the symbol at the current position on the tape, change the state of the control unit, and then move the read-write head left or right to a new position on the tape. Is this deterministic or non-deterministic? It is deterministic. What makes you say deterministic?
There's only a set of possible it could be.
Yeah. Yeah, you can't have multiple moves that say, when you see this, go do different things. So it's a deterministic machine in general. Defines at most one move for each configuration. That's what makes it deterministic. What are the limitations of a Turing machine? What is it that a Turing machine cannot do? If we had to put a boundary on, given that what we have seen here, what is something it could not do? Rephrasing that, kind of like what can a modern computer do that a Turing machine cannot do?
Math calculations.
Math calculations? Turns out Turing machines can do those.
Non-determinism.
Can a modern computer do non-determinism? It can do limited non-determinism with parallelization. But it turns out that we can model parallelism in a Turing machine.
It is a trick question.
It's kind of a trick question. There's actually nothing that a Turing machine cannot do that a modern computer can do. If we gave it a GPU of some kind, then its output could be interpreted in a visual manner, and we could create graphics. It's pretty wild to see. There is nothing a modern computer can do that a Turing machine cannot do. It is the simplest version of a modern computer. Okay, there is one limitation, which we will fix eventually, but it's that it's not reprogrammable. We can't tell a Turing machine how to run a program. Like there's no sense of run this program. It's already embedded on the input tape. It's already embedded within the control unit, what that is. We don't have the ability to build the control unit from instructions on the tape. But we will get there. So how does a Turing machine work? We're going to assume that it begins with its control unit in its initial state. So just like before, those states have an initial state. That initial state represents the initial state this is in. Say the same thing 4 times. We know that there is some information written on the tape. For now, we're going to assume that it starts on the leftmost character of the input. So what comes left of the leftmost character is a blank. But there's nothing that actually states that has to be the case. It will help you to be able to make an assumption that makes writing programs with a Turing machine a little bit easier. From that point, everything is deterministic. So we're going to look at the pair of what state is it in, what is the character on the tape. Based on that, we go through a series of transitions based on the underlying rules of the Turing machine that will do everything that a Turing machine can do. Read from the tape, write to the tape, move around on the tape, move through the states in the control unit. So we may be changing information on the tape, turning this input into some output. Since there's no other place for output to go, the output has to be on the tape itself. So either we have a Turing machine whose goal is to accept or reject, in which case it doesn't matter what's on the output tape at the end. But this also allows us to make a transducer. If we go all the way back to the first week of class, we talked about a transducer as a state machine that's able to produce some output. This is the first state machine that's actually able to produce output that's not just yes or no or accept or reject. We can put output in the system that is the tape at the end of termination. This is what allows it to do something like math. It will take as input the problem and modify that in some way to become the output that is the answer to that math. The process may terminate. That's kind of an important distinction. In other automata that we have written so far, there is no concept of non-termination. You read characters in a finite length input, and you either reach the end of the input and can accept or reject, or there is no transition defined on the current input symbol, which immediately halts and rejects. But in a Turing machine, that may not be the case. There's a special state in the control unit called the halt state, and we move to the halt state when the program has reached completion. So this is kind of the concept of we stop processing at this point, and we ask ourselves, if this is an exception or rejection scenario, we ask ourselves, are we in a final state? So when the Turing machine reaches a final state, we can halt and stop processing. If the transition is not defined, kind of like an NPDA or an NFA, we don't have to specify every transition. So if the transition is not defined that it wants to take, then we immediately halt. So yes, it's a partial function like an NFA. We don't have to specify every possible transition. That would end up becoming a huge nightmare with regards to Turing machines. We don't want to try that at all. So let's take a look at an example, program example. let's consider a Turing machine defined by these rules and a tape that looks like this. Let's run through what this Turing machine is going to do. We have our state definition. We have our input alphabet. These are the symbols that can be written. We have our tape alphabet, which is the input alphabet, plus the blank character that we can use to specify null or empty or something of the sort. So this symbol has the blank on it. This cell has a blank there. There's nothing written there, but it's not the empty string. It is the blank, representing there is nothing there. Our transitions here tell us if we're in Q0 on an A, we transition to Q0, write a B, and move right. If we're in Q0, read a B, we stay in Q0, write a B, and move right. This is overwriting a B with a B. This is the equivalent of a no-op. But we have to write something. If we're in Q0 and we reach a blank, then we should move to state Q1, which is our accepting halting state, and we will move left. So let's start with our read-write head pointed here. We start out in our initial state, which is defined nowhere. It's Q0. So we're in state Q0. We look at what the read-write head is pointing at. We see an A. So we're looking for a tuple on this side that is Q0 and A. We see that right here. This tells us what to do. We're going to stay in state Q0, write a B at the current location of the read-write head. And we're going to move the read-write head to the right. Back around, we're in state Q0 and looking at an A. So that is that exact same transition that we just did. We're going to stay in state Q0. We're going to write a B. And we're going to move the read-write head to the right. Back around, we're in state Q0. We're looking at a blank. So we're going to look through our transitions for that definition. Here it is, Q0 and blank. We're going to change the state to Q1. We're going to write a blank. So we're not writing something where that blank used to be. It's staying a blank. And we're moving left. We reached a halting state. Since Q1 is a final state, this tells us that when we reach this state, we are done. And the output to this would be the BB that's on the tape. So what does this Turing machine do? What is the program defined by these transitions?
Can you ask the question again?
Yeah, what does the program do? What is the program defined by these transitions?
Is it whenever we see an empty character, we terminate? Whenever we see a blank?
We do, we're making a single pass. We only ever move right until we're done when we move back left. So we're making a single pass from left to right. We know the string is only A's and B's because that's the input alphabet. What are we doing to the A's and B's that we see as we parse from left to right?
Making them B's?
Yeah, just turns all A's into B's. To B's, it does nothing. To A's, it turns them into B's. So this just takes the entire string of A's and B's, turns all A's to B's. That's all it does. Question?
So if we weren't in Q1 at the end, like we were at Q0, but maybe there's no possible moves, would we just reject?
Yeah. Well, you either reject if it's meant to accept or reject, or maybe the output when it terminates is the answer. But maybe you only want the answer if you reach such an accepting state, in which case we could say something like, we reject, this output is gibberish.
So do we only want the output if we reach a final state?
Usually, yes. Usually that tells us this terminated normally. It's kind of the same way that you can exit a program with flag 0 or flag 1 representing the program terminated normally or the program terminated with an exception of some kind. If there was output and the program terminated with an exception, the idea is that we don't know what happened with this output, but it's not the intended output of this program.
And then if you were in a final state, but you could keep making moves, are you like obligated to keep making moves or could you
Yes.
just accept it?
Yeah, you want to not have a transition specified in your actual final state like this. So the idea is we reach that final state, and because we got there, we're good. If there were further transitions defined there, we would want to continue to make those transitions until there was no transition defined. And the question is, are we in an accepting state? In which case we halt. Great questions. You can factor that out. Though you can turn that into a non-final state that does the thing, and then you transition into a final state where there is nothing to be done. So I think typically when we think of Turing machines, we think of there being a halt state as a single state that is, we are now finished. If you could do something in that final state, you can then make that into a, we're going to do that thing in a non-final state. And then when we recognize that we've finished doing that thing, we will transition to the final halting state. So we've already taken a look at exactly what happens, but here is the progression drawn out discreetly. Shh, don't let anyone know. I looked at 2 course equivalencies. I don't know if people know, I'm the curriculum chair for the department, and the last 2 equivalencies that I've looked at for transfer students, the catalog of the institution has spelled discrete math. DISCREET.
DES?
DIS.
Yes.
Yeah, discrete, like, shh, don't let them know. So it's just floating around in my head all the time now. Whenever someone says discrete math, shh, don't tell me that. Supposed to keep that secret. It's just funny because when I teach discrete, that's the very first thing I teach is the difference between discrete and discrete. One means sequential, integer value, whole numbers. One means keep it secret, keep it safe.
I just thought it was math.
Exactly.
Imagine if there's another class called discrete. And it's just the whole class, you're just talking really quietly about math.
Yeah, maybe that is. Maybe I made a mistake. That shouldn't have transferred at all. We don't have an equivalent course for that. Yeah,
Can you move more than one character right or left or only one at a time?
just one at a time. Although we will start to discuss equivalent Turing machines, things like what constraints can we relax on the definition of a Turing machine without changing its power. That's the next unit we're going to go into after we understand how these work. Is how can we make this easier to use? So one thing you might be curious about with regards to this is what does a transition graph look like? So we drew a DFA and an NFA, we drew an NPDA. Can we draw a Turing machine transition graph? And of course we can. So if we were to write the Turing machine from the prior slide as a transition graph, it would look something like this. It turns out that the edge, just like the edge in an NPDA, has 3 elements to it. It has the character that we read, the character that we write, and the direction that we move. Then the edge arrow tells us the state that we're moving from and the state that we're moving to. So all 5 pieces of information, nicely described. So I think it's actually easier to read than the NPDA. That said, Turing machines get complicated very quickly. So thinking about them as transition graphs may or may not be useful to you. But let's give you another example. Here is I'll give you a transition graph for a Turing machine. We're going to assume the tape has an A and a B in it, in that order. Read write head is pointed at the A. The question that I will ask you is, what does the machine do? What is the purpose of this machine? Here it is. Who wants to assert what this Turing machine does? Yeah?
To just move between the A and B.
Yeah, from Q0 to Q1 to Q0 to Q1 to Q0 to Q1. Let's take a look at that and explain it as we see it. We have on our read write head an A and a B. We start out pointing at the A in Q0. This tells us that from Q0, we're going to read the A, write an A, and move right. And that takes us to Q1. So we are going to, I'm just going to draw this because we're going to be right back here momentarily. We're at a B in Q1. That tells us to write a B and move left back to Q0, which tells us to read the A, write the A, and move right. So we're just going back and forth between these two states, doing the same thing over and over and over and over. Is there any way to halt this process? There is not. So this is our first case of an infinite loop in a state machine. Very simple infinite loop. It's 2 steps. But we will see that if we are not careful, Turing machines can go into infinite loops, just like the programs that we write. If I were to assert earlier that a Turing machine can do everything that a modern computer can, we can write infinite loops, damn it. And so we have the ability to do so. Just like with NPDAs, we can describe how Turing machines move through their states and move through the input with an instantaneous description. So to be able to make an instantaneous description of a Turing machine, we need which state the control unit is in. We need to know the contents of the tape. We need to know the position of the read-write head in that input. So we need to combine all of this information into one discernible piece of information. How could we do that? Turns out it's relatively simple, but I kind of want to zoom in on this because it's kind of small. So we're going to combine this information to a single string. We're going to write the contents of the tape, and then at the position of the read-write head, right before we get there. So before we put down the symbol the read-write head is on, we're going to write the state. So everything that comes before where the read-write head is, followed by the state, followed by everything at and after the read-write head. And that as a single string tells us all 3 of those pieces of information. Tells us the state, tells us the contents of the tape, and it tells us the position of the read-write head. Everyone buy that? That those 3 pieces of information are embedded in that one string? Any unspecified part of the tape is assumed to be blanks. In fact, we will see that it's a very bad idea to have blanks in the middle of important information. We need some other character that represents empty if we want to do that. We don't want null in the middle of this. For those of you who have messed around with C, what happens when you're trying to print a string, and in the middle of your string, there is a null character. It only prints up until the null. It's ambiguous between whether the string ends there or whether there is information past that. So we make the assumption that when we see our first null, that is the end of the string, because it's living in a character array. We make the same distinction here. We run into a blank. That means that's the end of the input. There's nothing past that. So try not to design a Turing machine that is over-reliant on blanks in the middle of things. Come up with a separate symbol that means some kind of separator character. If you were to have two numbers and want to add them, for instance, you would want some other character than a blank to represent separating those two pieces of information. You really only want blanks to the left of all of the important input and to the right of all of the important input, not in the middle of the important input. Okay, just like before, we're going to use the turnstile symbol to move from one configuration of a Turing machine to the next. All right, so let's write a transition. Here's the transition from Q1 on a C to Q2 writing an E and moving right. The tape contains A, B, C, D. Read write head is on the C. Go ahead and denote that transition using the configuration syntax. This should only be a single string, turnstile, single string. This is a single transition. What's the first string? Wants to give it to me.
Q1, A, B, C, D, A.
Close. So here's our input. We want to have the portion of the input that is before the current position first. So since we are pointed at the C, what should come first is the AB. Then we need the state that we are in, Q1. Then the remainder of the string, CD. This tells us everything we need to know. We know where the read write head is. It's pointed at the character that's after this, the C. We know what state we're in, it's Q1, and we know the entirety of the input, A, B, C, D. So this is the before. The turnstile tells us that we are going to be making a transition from here to the output from that transition. So what is the syntax that goes after this?
ABEQ2D.
ABEQ2D, I'd buy that. So when we made this transition, we moved right, so we should be one character to the right of where we were. Now we were to the left of the C, now we're to the left of the D. When we made that transition, we changed the C to an E, and we transitioned from state Q1 to state Q2. So again, this tells us everything that we need to be able to reconstruct the state of this Turing machine from that single string. And we could even reconstruct this entire transition from the beginning and the end. So we have everything we need in a reasonably nice syntax. How are we doing? Questions on instantaneous descriptions on Turing machines? Should be what I wrote. So as we've seen, it's possible for a Turing machine to go into an infinite loop. We're going to come back to this and study infinite loops in a lot more detail because it turns out they're really interesting. Okay, so one possible use of a Turing machine is, as we have utilized state machines up until this point, to recognize a language. So if we wanted to write a Turing machine program to accept the language, we're going to assume that the string that we want to determine whether it's in the language or not in the language is already on the tape. Blanks are on every space not used by the string. So all spaces to the left of the string are blank. All spaces to the right of the string are blank. Machine will start in its initial state, and the machine has been designed to be that language acceptor. So when this machine parses the string, it's able to determine yes or no, is it in the language defined by the transition function defined by the states. So read write head is positioned on the leftmost character of W. And then we can accept the string if and only if the Turing machine is in a final state and has halted. So it's reached the end of the string, it's done. But note that it doesn't have to do a single pass left to right. Now we can move left and right throughout the string as we go to that point. So we need to reach a final state and halt. Once we do that, we can determine it hits that halting state. That halt means that it's finished parsing the string. If it's in a final state, then we accept. If it's not in a final state, then we would reject when it is at that point. So it halts when it knows that it's done parsing the string. Yes, blanks not allowed in any portion of the string, already mentioned this. We see the ambiguity if there are blanks in the middle of the string as to whether there is something past that. If we had that ambiguity, we would always have to check for blanks. And we would never know if there is information embedded past the number of blanks that we've looked at so far. So if we want to reject, there are two ways to indicate failure. We can either halt in a non-final state, meaning that we have finished parsing the string and it is not in the language, or we could enter an infinite loop and never halt. That is an interesting way of denoting failure. It's just, all right, I'm going to continue to go into an infinite loop. You can design an infinite loop in a way that represents failure. We'll see why this would be potentially useful later on. So we're going to start writing a Turing machine program. And I keep needing to change this. This is just a language 0 plus. 0, 0 star says there's at least one 0. But let's spend the rest of class designing this Turing machine. So let's come up with the sets of transitions, states and transitions that we need to be able to recognize this. First thing you might want to think about, how many internal states do we need for this? Two. I like an example for 2. Why 2?
Well, just the way I'm kind of thinking about it, we need one for if it's a 0, and then we can put that state, just continue in that state.
Mm-hmm. How do we know how to halt? We need a separate I'm finished idea. Something like we're going to move to that halting state. So we need, if this is 0, 0 star, we need to ensure we see the first 0. That's the first thing we need to know for sure. We see a 0. We have the ability to handle additional zeros past that first 0. And then some way to say, the number that I saw was all zeros. So let's see if we can come up with that.
Yeah.
When reading the square for the final one, does it matter whether the rewrite head moves left or right?
Nope. It's not. That's a great question.
I meant to ask it usually because I noticed it said L and the R
Yeah.
just assumed is
So, yeah,
Yes, in Q2.
it can go either way. It doesn't really matter what the read write head is pointed to at the very end,
You got the.
as long as what's on the tape is the answer.
Okay.
In this case, we moved right to another blank. We could have moved left back to the string. I kind of prefer the left to the right, because then the read write head is pointed at the end of the string. That makes more sense to me, but it's not wrong either way.
Well, we can-
Question.
Last transition.
The last transition puts you into that halting accepting state. It says that we've completed, once we're done, we're in the blank. We read that blank, it tells us we're done, so we move into a transition to a state that says, we are done, we accept. If we had seen a 1 or something else of the sort, then we could make it impossible to get to that state. The only path to Q2 is through a string of all zeros.
Could we not just accept that Q1 and then finish in that state on a
We could, but usually we want the accepting state to be a transition-free state. This is the idea of pulling that out into its own state where the idea of halting is now its own state. When we reach this state, that is what signals or tells us that we are done and should halt.
Okay.
Otherwise, it's ambiguous between are there more characters to read and should we halt and accept? Since there were more characters to read, one of those could have been a 1, in which case we would have wanted to reject. And at that point, there's no way to halt from that state unless you make another state that is the halting state that you would read a 1 from or reject outright from there when you do read that 1. But it's fairly ambiguous. Wouldn't be the end of the world. All right, we'll come back tomorrow and do some more examples of this. Office hours starting now before homework.
Yes.
I'll take it.